So number 1 says, how many grams are equal to 3.8 moles of MgOH2? So I'm going to start with what I'm given. So that's 3.8 moles of MgOH2. And I'm going to need to use dimensional analysis to convert that into grams. So if I have moles, then I'm going to use moles on the bottom so that they'll cancel. And I'm going to change moles into grams. Now remember that 1 mole equals the molar mass in grams, right? That's up there on that chart. So 1 mole equals molar mass. So we're going to put a 1 down here on the bottom. But then we need to find the molar mass of MgOH2. So we have Mg, magnesium. We have 1 magnesium. We have oxygen. There's 2 oxygens. And hydrogen, there's 2 hydrogens. So we multiply times the mass of each one. And we would add them all together. And you're going to get 58.319 grams. So that's what goes on the top there. So for every compound, that number is going to be different because the masses are all going to be different. Since both of these numbers are on top, we're going to multiply them times each other. And so you would get 221.6 grams as our answer. Okay. So that's what went there. Number 2 says how many carbon dioxide molecules would fill 50 liters. So we're still converting. This time we're starting with 50 liters. So if we have liters, we want to cancel out liters. Liters go on the bottom. The only thing we can change liters into is 1 mole. So 22.4 liters, according to our conversions, is equal to 1 mole. But the problem doesn't ask me for moles, it asks me for molecules. So that means this is going to be a 2-step problem where I have to continue. I now have moles, so I need to cancel moles out. And I want to change moles into molecules. So once again, we have to look at our conversions. The top conversion says that 1 mole is equal to 6.022 times 10 to the 23rd molecules. So this time we have to divide and multiply, right? So we divide what's on bottom, multiply times what's on top, and we're going to get 1.34 times 10 to the 24. Don't forget your units, molecules. All right, so number 3 says, what is the percent composition of copper in copper chloride? So the first thing we have to do is find the mass of copper and of chlorine. So copper on the periodic table is 63.4546. Chlorine is 35.453. Now, if we want to find the percent composition of copper in copper chloride, we're going to need to divide the mass of just the copper, so 63.546, divided by the total mass. So after I multiply these and add them together, I get 134.1 33.452. That's the total mass. So then I divide. The last thing I do is multiply my answer times 100 because it's a percentage. And that's going to equal 47.26%. Okay, be careful on a problem like this because there was only one copper, so we used the mass of just copper off the periodic table. But if there was more than one copper, then we would have to multiply that and that answer would go on top. The total copper divided by the total compound. Number 4 says, what is the empirical formula for C6H12O6? Remember, empirical just means simplified. So what can I divide all of these? What common number can I divide all of them by and still have whole numbers for my subscripts? 6. I can divide them all by 6. And if I divide them all by 6, C6 divided by 6 is just C1. H12 divided by 6 is H2. And O6 divided by 6 is just 1. You do not have to include the ones. That's just so you can see that. Okay. So the empirical formula is the simplified version. Number 5 says, what is the molecular formula of a compound with a molar mass of 32.06 grams per mole and an empirical formula of NH2? So this is the opposite. Right now we have to figure out what to multiply times. So my first step is to find the mass of NH2. So I have N. There's one N. I have H. There's two H's. So if I multiply and add that together, you get 16.023. Now we're going to multiply the molar mass we're given in the problem. Divide 32.06 divided by the answer that we just got. And we get 2. So what that means is that I need to multiply this empirical formula times 2. So if there's only one N times 2, that's going to be N2. And if there's two H's times 2, that's H4. So it's a little bit more work to go from the simple to the not simple molecular formula. All right, so number 6 gets into reactions. So it says identify the type, predict the products, and balance. So I have an element aluminum plus another element chlorine. The only thing I can do with two elements is put them together. And so that's called a synthesis reaction. When two elements are going to form one compound. Synthesis. I'm putting them together. So now I need to figure out how to put them together. And you're going to have to look at your periodic table, right? So if we look here, let me see, back here at our periodic table, we have to remember that everything in group 1 has a +1 charge. Everything in group 2 has a +2 charge. Skip the transition metals. Everything over here in group 3A has a +3 charge. Group 5A is where it splits to being the opposite. So -3, -2, -1. So when we're trying to figure out what compound's made, we have to look. Well, aluminum has a +3 charge. Chlorine has a -1 charge. And so we need to make a neutral compound, so we switch those two charges. So if we have aluminum with a +3 charge and chlorine has a -1 charge, this 3 is going to end up with chlorine and this 1 is going to end up with the aluminum. So the product we actually make is AlCl3. Okay, So notice we can't just slap these two things together and call it AlCl2 because that wouldn't be neutral. There needs to be a 3 there because we checked the charges and switched them. So we identified the type of reaction, we predicted the products. All that we have left to do is balance. So when we balance our reaction, I'm going to divide my reaction in half at the arrow. And I can draw out what I have. I have aluminum. I have Cl2, which means there's 2 chlorines bonded together. And then I have AlCl3, which is Al with 3 chlorines bonded together. I have to make both sides equal to each other. So I have 1 aluminum on the left, and I have 1 aluminum on the right. So that's balanced right now. I have 2 chlorines on the left, and I have 3 chlorines on the right. So I need an additional chlorine on the left. But chlorine on the left doesn't come by itself, it comes as a pair. So I have to put both of them together. Now I have 1, 2, 3, 4 on the left side, and 1, 2, 3 on the right side. So I need another chlorine on the right side, but I have to add a whole nother molecule. Now I have 1, 2, 3, 4, 5, 6 chlorines on the right side and only 4 on the left, so I have to add 2 more. I do this until both sides are balanced. So now I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They're balanced. But I added another aluminum while I was balancing the chlorines, so I'll need to add another aluminum to the left side. 1, 2 means that I'm going to have a 2 as my coefficient for aluminum. 3 pairs of chlorine means I'll have a 3 for my coefficient of chlorine. And 2 aluminum chlorides means I'll have a coefficient of 2. That's my balanced reaction. Okay, we're going to use that reaction in number 7. Number 7 says how many grams of product should be produced from 5 grams of aluminum in the reaction above. So I know what I'm given. That's always going to go first. 5 grams of aluminum. I'm going to need to use dimensional analysis. So I have grams. I don't want grams, so I'm going to cancel grams out. The only thing I can convert grams into is moles. So grams of aluminum, moles of aluminum. I'm trying to find grams of product. My product is AlCl3. So I'm going to need to change from aluminum into AlCl3. I have to do that in moles. So I have moles of aluminum. I need to cancel out moles of aluminum. And on the top, I'm going to put moles of aluminum chloride. I don't want moles, I need grams. So I have one last step where I change moles of aluminum chloride into grams of aluminum chloride. So now I have a lot of numbers to fill in. So I have grams of aluminum. That's my molar mass. So 26.982. That's off the periodic table. The mass of aluminum is equal to 1 mole. Now I have moles of aluminum and moles of aluminum chloride. Anytime I have moles to moles, that's going to come from my balanced reaction. So I have to look at the coefficient for aluminum. That's a 2. And I have to look at the coefficient for aluminum chloride, which also happens to be a 2. And then last I have mass again. So my molar mass for aluminum chloride is 133.341. I added all that up off the periodic table, and that's equal to 1 mole. So here you have to divide and multiply several times so that you get 24.7 grams of aluminum chloride. Number 8 says, what is the percent yield of the same reaction above if 20 grams of product are actually produced? So here we need to know that percent yield is determined from what we actually make I spelled that wrong. Theoretical. So what I actually made divided by what I theoretically should have been able to make. That's a calculation. So we actually made this 20 grams right here. So 20 grams. Divided by we theoretically calculated in question number 7 that we should have been able to make 24.7 grams. Now this is a percentage, so we multiply times 100. And we get 80.97%. So last two. Number 9 is similar to number 6. It says, identify the type, predict the products, and balance. So now I have to see that I have one compound plus another compound. So when I have two compounds reacting with each other, that's going to be called a double replacement reaction. Okay, so how do we predict the products for a double replacement reaction? We are going to need to divide each of our compounds into its individual elements. So once again, you'll have to look for the charge on the periodic table. So lithium, because it's in group 1, always has a +1 charge. Sulfur is in group 6A. All of those elements have a -2 charge. Hydrogen is in the same group as lithium, so it has a +1 charge. And chlorine, we said before, has a -1 charge. So in a double replacement reaction, two parts of these compounds are going to switch places. Well, lithium is positive and hydrogen is positive. Two positives will never want to be together, so I will not put lithium with hydrogen. Instead, lithium will want to react with chlorine, which has a negative charge. So if I have lithium with a +1 charge and chlorine with a -1 charge, then they're both going to just cancel each other out and make lithium chloride, LiCl. Plus, I have sulfur with a -2 charge and hydrogen with a +1 charge. So they'll want to react together because they're opposite charges. So I have H. It's going to end up with a 2 because the charge of sulfur is 2. So when they switch, the 2 goes to the hydrogen. And then sulfur is just 1. So let's look at that. If I have this hydrogen that has a +1 charge, and I have this sulfur that has a -2 charge, this 2 ends up over here with the hydrogen, and this 1 ends up with the sulfur. That's how we got H2S. Okay, I'm going to erase that so I'll have some space. So then I need to balance this reaction. So I'm going to divide my reaction at the reaction arrow. I have Li2S, so that's Li, LiS. I have HCl, LiCl, and H2S. So I can draw out everything that I can see. I have 2 lithiums on the left, 1, 2, and only 1 on the right-hand side, so I need 2 of them. Okay, so now I have 2 lithiums and 2 lithiums. I have 1 sulfur on the left, I have 1 sulfur on the right. Those are balanced. I have 1 hydrogen on the left, but I have 2 hydrogens on the right, I'm going to need to add another HCl. That gives me 2 chlorines, which balances with the 2 chlorines that are on the right. So now that everything's balanced, I only needed 1 lithium sulfide, but I need 2 HCl, I need 2 LiCl, and 1 H2S. Okay, last question. What is the limiting reactant in the above reaction when 6 moles of Li2S and 4.5 moles of HCl are mixed? So my limiting reactant is which reactant runs out first. So I'm going to need to set up 2 stoichiometry problems. One for the first reactant and the other for the second reactant. I'm going to need to convert them both into my product. But here I have 2 products, so I'll need to pick one, either one as long as it's the same one. So for my first dimensional analysis setup, I'm going to cancel out moles of lithium sulfide, and I'm going to change that into lithium chloride. It's the first reactant, so I just chose it. It really doesn't matter which one you pick. In the second dimensional analysis setup, I have moles of HCl, so I'll need to cancel out moles of HCl this time. But I'm going to change it also into lithium chloride, just like the other one. Anytime I'm converting moles to moles, these numbers are going to come from my coefficients in my reaction equation. So if I look at the coefficient for lithium chloride, that's going to be a 2, so this 2 goes right here. The coefficient for lithium sulfide is a 1, so that 1 goes on the bottom. The coefficient for lithium chloride was 2, so we use that 2 again. And the coefficient for HCl, hydrochloric acid, is also 2. So 6 times 2 divided by 1 is 12 moles of lithium chloride. 4.5 times 2 is 9, but divided by 2 just stays 4.5. So we have to look at our answers here. Which one of these is the lower answer? 4.5 moles of lithium chloride. So that's not which one is the limiting reactant, because lithium chloride is a product. Instead, that means, because this is a lower answer, that means that HCl is my limiting reactant. So my answer is HCl. It is the reactant that will run out first because it makes less product. I could change these into grams as well. Either way, I'll get the same answer.